This presentation is part of the Bio 132 statistics workshops that you should watch before you attend the final workshop. This builds on the previous ones that you've seen, looking at means and standard deviations and the normal distribution, and introduces the concepts of probability and significance testing. As a follow-on, we'll then talk about the t-test as an example of a real statistical test. So this is the normal distribution that you've already heard a lot about, and this is the basis of a lot of significance testing that we do in biology. So you already understand the importance of sampling. So here we have a group of individuals, a population of blue and red individuals, and it's quite obvious to you, I would have thought, that you cannot get a feel for what the population is like by taking a sample of just one. If we took one sample, we would assume perhaps the whole population was red because we picked out a red one. Alternatively, if we picked out a blue one, we would assume the whole population was blue. Also, if we picked out two and we got a red and a blue, I don't think we would consider it reasonable to conclude that that population was 50% red and 50% blue. So our sampling has to be more sophisticated, and we also then have to put some metrics, some numbers on it, to tell us how confident we are in our sampling. So sampling really gives us population averages. If we have two samples, A and B, and we sample one individual from each of them, here we've got an individual of size 1 and another individual in sample B of size 2. We wouldn't accept that those are indicative of the population. Indeed, if we took two more samples, we'll see straight away we've got some variability in both populations. And it's not until we've taken lots of samples from both populations, got an estimate, or we can see quite clearly an estimate there of the distribution of the variability in both populations, and then we codify that, we distill that down into a mean. So we've got the mean size of A and the mean size of B, and then we can actually give the variability that we have in those populations a measure, as you've already heard in previous presentations, with the standard deviation. So averages can be displayed with means and standard deviation to estimate the variation within our samples and then assume the variations within populations. And as is implicit in that short presentation, and we might explore more in the workshops, the probability that you get a more accurate mean increases as you increase the sample size. And obviously, if you actually have a sample size that's equivalent to the population size, then you'll get exactly the population mean and standard deviation. But obviously in reality that will be time consuming, which is why we sample. So let's think of some simple examples of probability. Probability is simply the chance of an event actually occurring. So let's suppose we have a bag of balls, 100 white and 1 black. If we were to draw one ball out at random, then the chances that that ball was a white ball would actually be quite high. 99 times out of 100 we would get a white ball. However, if we were trying to work out the chances of getting a black ball, that's obviously much more unlikely. So only one time out of 100 would we sample a black ball. So straight away you can see in a very simple example the idea of odds and probability emerging. Those probabilities can actually be written in many ways, and you should be familiar with these and you should be comfortable with interchanging them, because you will see them written in different ways and you will be expected to use these interchangeably. So the probability in the previous example of pulling out a black ball was 1%, 1 in 100, or written as a proportion 0.01. You could also write it as a fraction, 1 in 100, or actually write that in words, 1 in 100. Or the chances to a betting man would be that the odds were 1 to 99 against pulling out a black ball. So remember, you should be familiar with those sort of terms. Now, we could start from first principles and do probability testing, but the fact that we know something about the properties of the normal distribution means that if we have a normally distributed population, we can take some shortcuts. We can use the things that we know, for example, that 68% of the variation lies within 1 standard deviation of the mean, and 95% of the variation lies within roughly 2 standard deviations of the mean. We can use these properties to actually take some shortcuts when we're statistical testing, and therefore make more powerful statistical tests. The problem is that we have to show in advance that these distributions are actually normal, because only then can we take the shortcuts. So normally in statistical testing we would do a test to show that the distribution of points actually followed a normal distribution. In practice, you might just plot them out and look at them and conclude that actually they looked normal, and therefore that was good enough, and that's fair enough in most circumstances. The problem you have, and the problem that the assumption that we actually violate in some of the examples we're going to show you, is that if you see what that curve actually looks like, the classic bell-shaped curve with a mean and then you're tailing off at both sides. If you only have a small number of points, say I only had 2 points to fit on this curve, I could fit a normal distribution to it, but I could fit any other curve through it. So a small number of points is generally not considered appropriate to do these type of tests on that are based on a normal distribution, because you're unable to show that they are in fact normal. These type of tests using based on a normal distribution and taking these shortcuts are referred to as parametric, and they're quite powerful because of these underlying assumptions. The alternative test, which takes makes no assumptions about the distribution of the data, are called non-parametric, and these often work on the basis of ranking the data or things like that, and you're probably familiar with non-parametric tests already. For example, the chi-squared test is actually a non-parametric test. We will, for the rest of this presentation and the workshops, be focusing mainly on parametric tests. But just bear in mind that if you are going to use a t-test, theoretically you should have tested or at least made some attempt to show that the data was in fact normal, and therefore you should not normally use parametric tests like this on data sets that are very small. So 3, 4, 5 data points is not sufficient to demonstrate normality. One of the things that we use when we're basing these on a normal distribution and for non-parametric tests are the probability cutoffs, the probabilities that we decree are the significant probabilities. And conventionally in biology, this P is 0.05, P is 0.01, and P is 0.001. These could be written also as 1 in 20, 1 in 100, or 1 in 1,000. And what we say in biology is that the p-value that we calculate from our significance test has to be firstly less than 0.05, or less than 1, or less than 5%. The next level of significance, which is 1 in 100, p is 0.01, p must be less than 0.01, or p must be less than 1 in 1,000, 0.001. And those are the ones that are conventionally used. So if you calculate a p-value above 0.05, then you would conclude that your data is not significantly different. And we'll go into the details of that in the next bit of the talk. So, p is less than 0.05. What does this actually mean? It has a number of meanings, and you should be familiar with it in your own mind. You should also be familiar with and be able to articulate what it doesn't mean. So it can mean that you have a 1 in 20 chance that an apparently significant difference that you see arose by random chance and is not a real biological effect. Another way of putting it is, because it's a 5% level, it means that while 95% of the time you'll be able to demonstrate a real effect if it exists in a population, 5% of the time you will not. So your data will say there is not a difference when in fact there is. The real statistical definition of what a p-value of 0.05 means is that there is a probability of 0.05 or 5% that you will fail to reject the null hypothesis when you should have done. You will see from these definitions that actually achieving a significant p-value is not proof. It just says how confident you are in the data, and the more stringent, the bigger the probability, then the more confident you are in the data. And you control the p-value. You set the p-value that you consider to be significant. And the lowest p-value that we use in biology is the 1 in 20, or p is less than 0.05. Anything above that is generally considered not statistically significant. So, p-values are based on the null hypothesis. What do we mean by a null hypothesis? Here are 3 null hypotheses. So you're interested in whether males and females are paid differently. So you say there is no difference in the salaries of a group of male and female workers. That's the first null hypothesis. If you're in medical research, you might have developed an anti-cancer drug and want to know if it works. You might test 2 populations on it, and your null hypothesis would be that a putative anti-cancer drug has no effect on tumour growth. Or, if you're being cynical, if we think these workshops are any good, you might set up a null hypothesis saying that attending the stats workshops will not improve your performance on Bio 132. So those are examples of null hypotheses. So let's think about using stats to reject the null hypothesis, using significance testing to reject the null hypothesis. So in this case we're looking at male and female salaries, and we're saying that there is no difference in the salaries of a group of male and female workers. So first of all, we test 50 male and 50 female individuals. That is, we basically ask them what they earn. So the averages came out as male earning 53,000 and females earning 50,000. Crucially, when we did a stats test on this, let's say we did the t-test that we're going to do in the next section, we came up with a p-value of 0.03 or 3%. So what does this mean? This means this is less than the first cut-off point of 5%, or p is 0.05, so you would conclude that males are significantly better paid than females, quite rightly based on the statistics. And so you reject the null hypothesis up here that there is no difference as incorrect, and establish the fact that there is in fact a difference between males and females. However, you have to be cautious. Remember, you have not proved that males earn more than females. You have just shown it's highly likely, and you know the level of likelihood that males earn more than females. If you sampled 100 times, or did this experiment 100 times, on 3 occasions you would not reject the null hypothesis, okay, because p is 0.03. 97 times out of 100 you would show there was a difference. 3 times out of 100 you would show that there wasn't. So that's how confident you are in the data, and that's how much you can stand up and be confident in it in front of other people. 3 times out of 100 this result would be wrong. So you can see that probability just gives you significance, just gives you the probability of how confident you are in the data that you've got. And here's an example of the sort of error that you can make that we've already alluded to in the previous section. It's called a type 1 error, or a false positive. So let's assume there's 2 populations which don't differ in resistance to an antibiotic. You're going to sample them and do a statistical test, and you set the required stringency to 0.05%, or p is to 5%, or p is 0.05. You get all your samples and you do a t-test, and you get a value of p is 0.03 from your test, which is less than the required value of 0.05. So you rightly reject the null hypothesis, which was that there was no difference in resistance. In fact, as I've already said, in reality, there is no difference. You were just unlucky in getting one of the 3% of times when random factors did give you a significance. So that's an example of a false positive, and the p-value tells you not whether they are actually different or not, but how many times you might expect to get a false positive. So how do you avoid these type 1 errors or these false positives? Well, you have a number of options. You could increase the stringency. If you had set the required value to p as 0.01 or 1%, you would have rightly accepted the null hypothesis. You could increase the sample size, obviously, but that might be impractical, or you could repeat the experiment. If you did the experiment independently 3 times, it's highly unlikely that you would get a p as 0.05 each time, given the reality that there is no actual difference. So you would compound the probabilities, and I think if you did the experiment 3 times, it would be about 1 in 100,000 chance that each of them would randomly give you a significant effect, when in fact there was no significance based on this variation in the population. This is actually an important issue. Weak statistical standards implicated in scientific irreducibility is just recently been published in this Nature paper, where what they're actually arguing is that the problem of published data often being unrepeatable is because scientists weren't stringent enough with the cut-offs they chose. I won't go into the detail, but they basically say that 0.05 is not, on its own, is not sufficient, and that you should have a higher stringency or use a completely different type of statistical test. I don't fully understand that, but we won't go into it here, but it does illustrate the issue of being cautious about your data. The other type of error is a type 2 error, or a false negative. Let's say you test 2 populations for resistance to the antibiotic, and again the null hypothesis is that there's no difference. Let's say, for example, that these 2 populations are actually different, and you set the required stringency as before to p as 0.05, and now you get a value of p as 0.13 from your test, and you accept the null hypothesis, concluding there's no difference because the p that you got, 0.13, is above the significance value of 0.05. So you conclude there's no effect of your drug. But in fact, there is a real difference in resistance. You were just unlucky in getting one of the times when the random factors gave apparent non-significance. And again, here you can see that if you're cautious and you repeat this experiment, then you probably, statistically, you would get a difference the next time. And so repeating experiments, as well as changing the stringency or increasing the samples, will help you avoid these type of errors. So thinking about type 1 and type 2 errors, or false positives and false negatives, which is the most important depends on the type of question you're asking. So here's an example. Would you rather have a sensitive fire alarm that goes off all the time, even when there isn't a fire? That's a false alarm, a type 2 error. Or would you have a very insensitive fire alarm that doesn't go off when there is a fire, which would be a type 1 error? So you can see there that probably you'd want B. You wouldn't want B. You wouldn't want to miss a fire. So you'd set up your experiments to have more type 2 errors and to minimize type 1 errors. So you could think about the sort of experiments you do and which sort of data you get, and whether you're more likely to want, if you like to err on the side of caution, towards a type 1 or a type 2 error. Throughout this, hopefully you've seen that the important thing is that you have ownership of the data and the statistical levels and their interpretation. And again, with the type 1 and type 2 errors, the false positives and the false negatives, you have ownership over which is the most appropriate and to your interpretation.